again, I'm student Mohammed Esbal. In this video, I'll be taking through carbocation rearrangement in the reaction of 6,6-dimethyl 2-hexanoid. Before going through this reaction, I would like to look at its overall reaction, because this overall reaction is actually going to show us how our product will look like. As you can see, we have not gone through the mechanism, but we already know that at the end of that mechanism, our product will be 2-chloro 2,6-dimethyl hexene. When 6,6-dimethyl 2-hexanoid got reacted to hydrochloric acid. So in the reaction mechanism, we are going to see how this happened. This wasn't magical. There must have been several steps through which we got 2-chloro 2,6-dimethyl hexene. So let's dive through and see how this happens. So now the first step of the mechanism is called a protonation of 6,6-dimethyl 2-hexanoid. So now look at this step. This step is a bimolecular step because to the reactant portion of this reaction, there was bimolecular changes, which means there were two changes happening at the same time. Like for example, the hydroxy group that is attached to this hydrocarbon chain protonated, which means it stood off hydrogen from here, it brought it to itself, and this chlorine stood off the 2 electrons that the bond between hydrogen and chlorine encompasses of. Is still it. So now, just from what is happening here, we can categorize this 6,6-dimethyl 2-hexanoid as a Bronsted-Lowry base. Why? Because we know that it's tilting off proton, and from the definition given by Bronsted-Lowry, a base is a proton acceptor and an acid is a proton donor. Considering the fact that the hydrochloric acid or the hydrogen chloride is donating hydrogen to this hydroxy group that is attached to the hydrocarbon chain, we can consider this hydrogen chloride or this hydrochloric acid as a Bronsted-Lowry acid. So now, looking at this arrow facing it forward and backward actually indicates that the reaction is a reversible reaction. And if we say that the reaction is reversible, that means this product 1,5,5-methyl hexyl ions could possibly be reconverted to 6,6-dimethyl 2-hexanoid when its structure gets manipulated. And then look at the other steps and see how we actually reach to this 2-chloro 2,6-dimethyl hexane. So looking at step 2, this step is known as the ozonium ion dissociation step. In these steps, these ions, as you can see, called the ozonium ion, because in that first step we said that this hydroxy group got protonated, which means there are additions of protons. So when proton is added, the net charges, when proton is added to this hydroxy group, oxygen net charge will no longer be 0, it becomes +1. So now, because of this charge, we can consider this 1,5,5 methyl hexyl as an oxonium ion. An oxonium ion is an anion that consists of oxygen. An oxonium ion could be monoatomic or polyatomic, but we are not really discussing that. So now in this step we said we are actually looking at how these oxonium ions will dissociate. If you hear the word dissociate, mean break off, detachment. We're talking about separation. So now these oxonium ions will dissociate, which means this water molecule that is formed will break off on its hydrocarbon chain. So now see this arrow indicates that the bonds between oxygen and this carbon right here will be broken off. So now the two electrons that this bond encompasses of will get attached to the oxygen as lone paired or non-bounding electrons. So that the second step is very slow step, because we can consider this step as a rate determining step, because this step will actually result into the formations of a carbocation. So let's see how this happens. So if this detach from this hydrocarbon chain, the carbon right here will now have only 3 bonds. So if carbon only have 3 bonds, it will have a net charge of 1. And any carbon that have a net charge of 1, it becomes carbocation. That charge that is attached to that carbon is called cation. So to describe that carbon, we can say carbocations. This specific way of calling that ion, we can say carbocation, or some author may say cabocation. But that could be due to their phonetic skills they have in pronouncing words using syllables. So now, see, this arrow is a one arrow telling that the reaction is irreversible. So if we detach this water molecule that is attached to this hydrocarbon chain, now we are left with a secondary carbocation, as I said earlier, because this carbon is bounded to a hydride, is bounded to this carbon plus this carbon. Now water becomes our byproduct. We don't really need water. From the overall reaction, we know that we are looking for alkyl halides as our product. We are not looking for alkyl halides plus water. So water in this case is considered as a byproduct. Now look at the third step. The third step is just converting from secondary carbocation into tertiary carbocations, because secondary carbocation is less stable than a tertiary carbocation. This is the reason why we are trying to convert it from a secondary carbocation to a tertiary carbocation. Remember, when we want to convert a secondary carbocation into a tertiary carbocation, we have to do something called shifting. So we could possibly shift a methyl group, or we could possibly shift an ethyl group, or even a hydride, depending on how our product was like in an overall reaction. Since we know that in an overall reaction, red here was our chlorine, or was our chloride or chlorine attached red at this point. So what happened in this case, there will be something like methyl shift. So now, as you can see in this step 3, the methyl group that is attached to this carbon here we shift to where the carbocation was, or where the carbocation is, as you can see. So now when this material get attached, there will be bond formation, because once there is bond formation, it indicates that there is no cation anymore, because we know that here is carbon, and here is a hydride. So if we attach methyl group here, now this carbon now we have a net charge of 0. Now we have shifted it. See how it looks like in a product. This is 1,5,5 trimethyl hexyl cation. So this is it, and this is the last step, which is the chloride ions nucleophilic attack step. So in this step, the chloride ion will serve as our nucleophiles, and this 1,5,5 trimethyl hexyl cation will serve as our electrophile. So just from their names, we can also categorize them as either Lewis acid or Lewis base, considering that this 1,5,5 trimethyl hexyl cation is accepting an electron pair, we can categorize it as Lewis acid, and considering that this chloride ion is donating electrons paired, we can call it Lewis base. So now this chloride ion is a base and also an electro and also a nucleophile. Why can we call it nucleophile? Because it is nucleus loving, or it wants to form bond for it to get more stable than it is. But this guy needs electrons to make a bond, and this guy wants to be in a bond so that it gets more stable. The essence of two elements bounding together is for them to get more stable, or for them to get a complete orbit. So chloride ion standing by itself, that even though chloride ion needs 8 electrons, but when it stands alone, the day is not stable except it make a bond. That's the reason it's acting. This chloride ion is acting as nucleophile, because it want to have a nucleophilic attack on this 1,1,5 trimethyl hexyl cation cations. So now this will get attached to the car, making a bond, and when we get attached making a bond, now this tertiary carbocation will get lost. So when it get lost, now our chloride ion get attached in this position. So now after attaching this, our end product will go exactly to where we begin from, which was 2-chloro 2,6-dimethyl-hexane. So now finally, from all these steps, we are able to get the same product in our oil reaction. Thank you.